final exam. So I'm going to make a Piazza post about this, but basically, so see Piazza for the final exam policy, but peer tutors are exempt if you've done your 10 hours. Okay, if you're not a peer tutor, but you have a 93 or above, then you'll need to do section 4 of the final. And it is a take-home. So you can turn it in electronically or slide it under the door for your TAs at EB2 3222. And it is due the day of your final. So you can post it on Piazza, or actually we'll make a Moodle turn in for it so you can also just upload it so you don't even have to show up. Everyone else, you will also have section 4 of the final. It'll be due at the final. You can also turn it in beforehand if you like. And you have to do one other section. So as we've talked about several times in class, we'll have 3 other sections that correspond to each of the sections that we've had tests on. So homeworks 1 to 3 were on test 1. And section 2 was on homeworks 4 to 6. And section 3 was on homeworks 7 to 9 and corresponds to test 3. You have to do one other section during the final, and this fourth portion is take home, and it's due at the final. You don't have to turn it in like the moment it starts, so if you do a section and you want to work on 4 some more, you could, but I don't know why you wouldn't finish it before you got here, so you could leave as soon as possible. Another thing that we are doing, because we're awesome, is that you may also go to the December 11th final exam if you would rather do it then. I don't know about you guys, but I really don't want to be here on December 17th. That's when our exam is. So if you would like, you may come to the December 11th exam. It's in this room from 8 to 11 a.m. I am going to make a post on Piazza. You have to tell me which section you're going to do of the final. You may also take all 3, and we will use the best one to replace, if it is better than an original test grade, we'll use that to replace your original test grade. We'll do the best one. So you can plan to do 1, 2, or 3 of the sections. I don't care how many you do, but you have to do at least one besides the take-home. So everybody has to do the take-home unless you're a peer tutor. And if you're a peer tutor, that's all you have. I mean, if you have a 93 or above, that's all you have to do. And then everyone else has to do that take-home section and one other section of the final. Yes? It's part of the final. Can you ask that question again? Yeah. That's it. Yes, everyone takes 2 sections unless they have a 93 or above or they're a peer tutor. And everybody has to take section 4. So you can take more than 2 sections, but you have to take section 4 in one other section, and you can do the other 2 if you want. I have not posted that. Yes. Tonight. Yes. I actually almost posted it, but I didn't hit post on my thing in my office. So I had it written up. I just came over here because I had a meeting right before, and I didn't get back on my computer. And I might have closed the window, so I'll probably have to write it again. So anyway, another question? On WebAssign? I actually just turned off the inclusion on WebAssign of the lab grades because I haven't put the lab grades in yet. Because I have to write a program to parse them, and I haven't done it yet. I'm sorry. Yeah. So I just turned that off, so it'll calculate your grade without the lab grades. So if you've done them, you're going to get credit for them. Yes? That's right. The guaranteed C policy is you have to take all the exams, all the homeworks, and rework everything until you get at least 70%. And you have to do special tests and rework them until you get 100%. If you do all those things and you hand them to me at the final exam, if you happen to be on the cusp in between two grades where I'm drawing the line between like B plus and A minus or some other lower grades, I will bump you up if you turn in the guaranteed C material, but only no more than 1 point. So I won't give you more than a point for that. Yes. The special tests are posted on Moodle. It's called Special Tests, and they're at the top. You can print them out. Yes. You're supposed to finish everything by the 5th, but if you finish it by the final, I'll still take it. But you should have anything you need checked by TAs. You need to do it by then, because who knows if they're going to have any office hours after that. And I'll be writing a grant proposal, so you might find me sometimes. Okay, any other questions about this? So I will post on Piazza. You have to tell me which sections you're going to take. You can change your mind if you want. So if you come and you want to take some more sections than what you said, that'll be fine. I'll have some extra copies, but I just want to know how many to print, because I've printed all of them in the past and then like gone home with like a whole bunch of blank paper. And I really like trees, so I'd rather not do that. Okay? Any other questions about logistics for the final? How come nobody's dancing? Isn't this nice? Okay, that's better. Okay. All right, we got 2 more classes. By the way, I realized that we didn't talk about finite state machines, and some of that's on homework 10, and homework 10 was due yesterday. But as you know, you can ask for an extension, or I don't know if it was due yesterday. Some people were complaining. Can't wait. Okay. So we're going to talk about finite state machines now, and then we will do Hassse diagrams at the end, because you've already seen some Hassse diagrams. We did some last time, and we also had them on the counting tutorial. So we'll start with finite state machines. There is a finite state machines packet on your Moodle. So be sure to print that out and look at it. It's very, very useful. Okay, does anybody know what a finite state machine is? And if you don't raise your hand, I know you're lying, because a bunch of you are in 216. Okay. Who wants to tell me a definition? How about you? That was a machine. It's a machine with finite states. Like,
it's a machine that has, like, so it has a finite number of states, and it has a set of rules that govern transitions from one state to another.
That's great. You actually started having the parts that we need. We have states and we have transitions, right? And states are defining different states. So it's actually hard to define it without using the words that are in the definition, and there's a finite number of them. And the transitions tell how we move from state to state. So what do we use finite state machines for? Okay, so phones actually have things like finite state machines in them for all the buttons that are on them. So every button that you use on every device has something like a finite state machine that has a table that it used to look up, according to what state I'm in now, what do I do when you hit this button? So for example, an iPhone has exactly one button on it, right? Well, it has more than one, but it has one main button. And when I hit this button, it does different things according to where I am. But it's still a finite number of things. And it has a table to look that up. So wherever I am, it decides, okay, now since I'm off, if I press the button, that means turn on. If I'm on, it means go home. If I'm in an app, it means get out of this app. So it has different meanings, but it's basically a lookup table of what I'm going to do. And the state is the status, the current status of whatever world you care about. So that's what the word state actually means. So we have in games, for example, whenever you save your game, what it's going to do, it's going to serialize. That means turn it into a list. Everything in the game world that is different than like the basic background. So it's going to write out into a file like all the stats for all the enemies, your score, your health stats, everything. It's going to write that into a file. So when you load it back up, it's going to bring that up. That is a game state. Okay? So sometimes we actually talk about states in like regular conversation. So people come up to you and they say, how you doing? And you say, fine. That's a state, right? It's a state I care about. If I say it that way, does it mean fine? Probably not. It means stop bothering me, I'm trying to do some work. Just ask my husband. Okay, and sometimes you say, really good. And that implies something, right? Like you actually want to tell somebody. You know, so we actually infer some things. So we know states of people, and if you know someone, you know what their answers actually mean. So we use them all the time. And transitions these are places where states can change. So if you say, hey, how you doing? And you happen to be this is an example you might not even recognize, the Publishers Clearinghouse award deliverer with a giant check. It doesn't really matter what the state was before, right? The transition is, oh my goodness, I just won a lot of money. Okay? So we might have some transitions that all go to the same state. But most of the time, most of our transitions are in between minor state changes. Okay. And these are really super abstract. And you can think of it that actually the way we're going to implement most of this is by table lookup. So we actually have some pictures of how we represent finite state machines, but what we actually do in the computer is we usually have a big fat table that tells us what the states are, and then it lists columns for all the things that might give me transitions, and then it tells me what the new states are. And mostly what we have in our table at the top are different kinds of input. So most of the time when we're talking about finite state machines in computer science, it's because we're going to get some kind of input, and then we're going to change the state based on the input. So let's go to a video game example. So what are some kinds of input that you might have that might change the state of the game? What'd you say? I might place a block. What game are you thinking of? Minecraft. Okay. So if I'm in the state, so in Minecraft, the world state's pretty complicated, right? So it's going to be like where all the blocks are and where all the characters are and how much stuff you've got in your inventory and all that kind of stuff. So it's a big complicated state, so I'm going to give it a number because that's what we're actually going to do when we make states in computers. We're going to say, well, that's a really complicated state. I'm going to map it to a number, and this state's going to be state number 1. Because if I actually wrote down all that information, I wouldn't fit it on the page. So, but the state actually is going to be, like I'd have also a table that points from the numbers to what the actual world state is, so I could really look it up if I needed to. And then if I place a block, then it's going to change to state number 3, whatever that happens to be. So I'll have a table just like that for all the possible inputs that I could get from a user. So you can also, what else can you do? You can break a block, and maybe that would go to state 5 or something. So you'd have a table that will change the world state according to all that stuff. Now, I might not do that. I probably wouldn't do it in Minecraft because it's such a big set of states that you could possibly have. So I probably wouldn't do it with Minecraft. But I probably would do it with Pac-Man, for example, right? So each of the ghosts could have a state that it's either in the regular state, right, which is the chase state. So let's do Pac-Man because Minecraft is awesome, but it's a little more, I wouldn't use a table for it, okay? So I'd probably have a table, but it'd be more generic. So it would say the state would actually just be what position I'm actually at. And then at this position, I would then write a 1 for having a block there. Or not 1, I'd write actually what type of block got placed. So for that, I'd have just a giant array of all the possible places where blocks could go. And then I would have a set of bits that would tell me which kind of material was there or was not there. Okay, so let's say for Pac-Man Ghost. So we're going to make a ghost state table for Pac-Man. Okay, so we know that there's one state we're going to call Chase. By the way, we get to make the names of states. So you can name your states like 1, 2, 3, 4, 5, or you can give them names that will help you remember what the transitions are supposed to be. And that is what I would recommend that you do. So actually, let's draw this with a diagram, and then we'll turn it into a table. Because we often think more in diagrams and transitions than we actually think of in a table. So tables are great for computers, and they're also really fast for lookup, but not so great for our brains. Okay? So computer brains are different than people brains. So let's do the people brain version, and then we'll do computer brain. Okay, so we're going to think, okay, they're in the chase state, unless what? Unless what? You eat the power block. So Pac-Man eats the power block, or pellet, or whatever you call those things. Okay, and then they go in the what? They go in the flee state, right? And then after a certain amount of time, they go into what state? Actually, after they go to flashing state. Thank you, people who play old games. This is like the best game of all time. Actually, Miss Pac-Man is a little better. You knew I was going to say that, right? Baby Pac-Man's not very good. Okay, so they go into flashing state, and then what can happen? That's right, okay, so they go to eyeballs. So this is a certain amount of time elapsed. Yeah, they have to be in flee or flashing. If they get eaten, they turn into eyeballs, right? Okay, what else can happen? They also can go to home, right? But they're still in the same state, so we're still going to draw the same picture for them until a certain amount of time elapses after flashing, right? Then they go back to chase. And in fact, they probably have like an incubation time in home. So like, let's just call that like the home state, because they're definitely going to get in there. And so that's just going to wait a certain amount of time, and then they're going to go back to chase. And so this table will tell you, like if I'm writing the program for Pac-Man, I can decide what to do with it according to all the inputs. So if I get an input, I can check the state of the ghost and see if I need to change it, or if he needs to be moving away from Pac-Man or towards Pac-Man, or towards home. When they go to flashing, they do start going home, don't they? Yeah, so this is just when they get into home is all I meant. So that's what the transition is if they're in home. So the transition's not actually what they're doing. So in a game, objects have actions. Those aren't their states. The actions, like we're just giving names to these because these are the actions that they ought to be doing while they're in that state. But the state is just, I'm afraid of Pac-Man right now. Okay, they can go from flashing. What changes that transition? Okay. Okay, so we have a pretty good diagram for the ghosts. What happens if he runs into the Pac-Man and the Pac-Man's out of power? Kills the Pac-Man. So if he's in the chase mode, then that means he's not in flee mode, because if he's in flee mode, then Power Man's already eaten the power block. So if he's in chase mode and he runs into Pac-Man, that causes Pac-Man to die, right? Pac-Man life, they lose a life. But he's still chasing, right? So this is kind of like a little offshoot onto Pac-Man's state diagram. So it's really like you should ignore that for the purposes of this diagram, because he's still going to chase, right? Whether or not he runs into Pac-Man. He's going to run into Pac-Man and then still chase him again as soon as he comes back up. Yeah, okay, so when he runs into Pac-Man, he goes back home. So now you know if you want to make a game, you have to make big diagrams like this. We have the same kind of diagrams for non-player characters in lots of games because this is the easiest thing to program. And AI is usually the last thing that people do for their game, unless that's going to be the main thing that they're selling it for. Anyway, so finite state machines are also used for like Coke machines, for example. So they don't have like a general, well, they probably do now, but they didn't used to have like general CPUs in a Coke machine. They would just have a finite state machine, which is really easy to build a circuit board for, that would just decide, like based on which coins it got, like what state it was in. So let's do a little one for that, and then we'll make a table. And let's make Coke cheaper just because we're in fantasy land. I don't like it being $1.25. I don't know about you guys. It would be cool if it was like 50 cents. Let's make it 50 cents. What'd you say? You're gonna. Okay. Yeah. All right. So this is our, Dreamland Coca-Cola machine that we can buy things for 50 cents. All right. So now we have a start state, and most finite state machines do have start states. And that means nothing has happened yet. So it's like the default initialization state. And then we can get some different kinds of coins. We're not going to take any pennies because that's a pain. Our finite state machine would be too big. Okay? So we're going to take some nickels. And what would you like to call this state? 5. That's a great idea. Okay? And how about if we take a dime initially? We can call that the 10 state. So we can call the states how much money we've gotten so far, and that'll make it easy for me to figure out what to do when I get different coins. Because then I can make the state just be whatever the state name was plus the coin that I got. All right, so we're also going to take quarters, and we're just going to consider it a bonus if we get some Canadian dollars. Oh, no laughs for that. Okay. What say? You were saying no to pennies because we don't want to make that diagram. Okay. All right, if we get each of these, now if I get 10 cents, if I get 5 cents again from this state, that 5 chain is going to be 10 of them, right? So if I keep doing 5s at the top, I'll have 10 of those. But let's go down here. So if I get 5 cents from 25, I'll go into 30 state. So see if you can make this table on your paper, and then we'll check back together to tell you. And that is Friday's reading day. Everybody knows that, right? And you can't wait for Friday, right? Okay. Friday we have a graduate school recruiting day. So it's going to be an all-day event from 9 to 5. And later, actually, there'll be a reception and some downtown stuff because Friday is First Friday. So we're inviting students from the region to come and visit NC State and see what it might be like to go to graduate school. So there'll be some lab tours and a little talk about grad school and things like that. And if you're interested, I'll post on Piazza like information for signing up, but we'd love to have you there. So we're really interested in keeping the best of you for graduate school. And even if you're not the best, if you're super, super interested and you work really hard, we'd like that too. So anyway, so it's our graduate recruiting day. And I just wanted to let you know about that because I'm organizing it, and I'd like to have some people there. So we have 9 students coming so far, but I'd love to have a lot more. So we'll feed you lunch. If like all of you sign up, I'll have to say no to some of you, but probably 10% of you will sign up, and that'll be fine. First Fridays, Yeah, we're just going to take the visiting students downtown, and you can go with us if you want. And it would be awesome if some of you come also so you can tell, the visiting students what it's actually like to be at NC State. It's different to be a grad student, I can tell you that, but it's still the city's the same. Okay, so 01 is another language we might consider, and the sigma with a star on it, the Claney star, is all bit strings, including the empty string. And we're given the language all even binary numbers with no leading zeros. So the first thing we're going to do is make some example numbers. So 0 is an even number. That's there. The empty bit string, I'm not going to count that as being even because it doesn't make any sense. Let's see. So 2 is also even, and 4, and 6, and 8, and 10, Okay, there's something that these strings have in common. What is it? They all have a 0 at the end. So, we might want to start with the start state. And then if we get some 1s, so we're going to start at the left side of the string. That's what we do. Okay, so we're going to get some 1s at the front end. We don't care how many of them we get. We're still not an even number, right? But if we get a 0 after that, we're happy. So we put a double line around a state that's an accepting state that we will take. And we're going to call this the even state. And this start state is also an odd state, sort of. It's either the empty or odd state so far. But we have some other possibilities. What if we get some 1s, and then we get a 0, and then we get some more 1s? Do you want to make a new state or go back to a state we already have if we're in even state and we get a 1 after that? Let's go back to the start after we do that. Because then if we get another 0, we'll go back out to even, and that seems pretty good. What about if we get a 0 when we're in the even state? If I get a 0 after a 0, stay. Okay, and now, do we have everything? Yeah, because we have a 1 and a 0 both leaving the start state, and we have a 1 and a 0 both leaving the even state, and that should cover everything. Let's check a few of our strings to make sure that all the ones we've listed will actually work with this machine. Okay, so if making a finite state machine is not some process that I'm just holding in my brain and I'm going to check yours. It's a creative process. You might make a different one than I would make, and it could still be correct. So I like to try to make them efficient and have the fewest number of states possible, but you could have 20 states and it'll be fine. Yes? Does this allow leading zeros? Yes, it does. It does allow leading zeros. So we might want to change it. So let's make a new one. And if we get a 0, we're going to go to the even state. And if we get a 1, let's go to the odd state. Then if I get a 0, let's go to the even state. And if I get a 1 here, stay. If I get a 1 there, go to the odd state. And if I get a 0 here, stay. I'm sorry, what was that question? Yes, there should be a 0 on the arrow that goes from start to even, because I can have transitions that take nothing, but we don't want the empty string. That's what we decided at the beginning. Yeah, I still have a leading 0, but I want to accept a single 0. So you're right, I need to fix it. I didn't actually totally fix it. So I need to actually make a state that just takes the 0, a plain 0, right? It doesn't count as a leading zero because that's not an extra one that you don't need. Well, I don't mind if there's leading zeros. So let's just leave it. Here's how we're going to solve this. Since I made up the problem, yeah, sure, why not? Yes, you may do that on the test, and you'll get some partial credit. I get partial credit. I'd say this is 90%. Okay, whenever, this is for all of life, whenever you can't solve the problem that is in front of you, that doesn't mean stop. It means change it to a problem you can solve. And then you might be able to fix that later. Now, there is a way to fix it, but it's called a non-deterministic finite state machine. So I'll show you how we're going to fix it. So that was, my joking way to fix it. But my real way to fix it is this. We actually have a way to represent this. So this is a machine that just takes zeros. And I'm actually going to call that the zero state instead of the even state. And then this is going to be my odd state. And then if I get a 0, I'll go to a new even state. And if I get any 1s, I'll stay in there. If I get a 1 there, I'll go there. And if I get a 0, I'll stay here. So that's how we do it. We can just make a separate machine that deals with a 0. And they can go to separate places. So that deals with the leading 0. So this is not non-deterministic. It's still deterministic. So what deterministic means is if I get an input alphabet character, that I know exactly what state I'm going to go to. That's what deterministic means. So does anybody in here believe that your fate is predetermined? Anybody? No determinists in here? Okay, so in a deterministic finite state machine, the fate of any string is predetermined. Okay? In a non-deterministic finite state machine, there are transitions that are allowed to happen whenever they feel like it. Or there may be more than one choice for a transition. And in that case, we don't actually know what state we'll be in when we get a particular character. And you can imagine that computer scientists don't really like these things because you don't actually know what to do with it, because it might be in this state or it might be in that state. So in general, we're going to try to draw deterministic state machines. So what we need for a deterministic state machine is exactly one choice for each letter in the alphabet for a state transition from every state. So another way to draw this in a non-deterministic way would have been to go to the start state and to have an even state and an odd state. So this is a non-deterministic state machine that will do the same thing. So this epsilon is the empty string, and it's going to randomly figure out that I'm at the end of the string and jump to the final state whenever it figures out that it's at the end. That's non-deterministic because I can't actually tell that I'm at the end of the string until I'm at the end of the string. So I can't make a table for this. It's just sometimes I can make a table. I can make an epsilon column and say sometimes randomly go to the final state when you get nothing. Okay? We don't like that. So this is non-deterministic because we can't tell what's going to happen. Anytime I get into the even state, I could jump into the final state. It's still a diagram that describes what happens, right? You can't get in the final state unless you're in an even state. But we just can't predict using a table when it's going to happen. Okay, so we have a few rules for writing regular expressions. So basically, there's a cool proof that says if you have a regular expression, you can make a finite state machine for it, and vice versa. If you have a finite state machine, you can make a regular expression for it. So let's actually give a couple of regular expressions and then try to make some finite state machines for them. But before we do, I'm going to give you a few rules. So something like AB means A followed by B, just to make sure. So we can concatenate strings, and it means exactly what you think it should when we look at regular expressions. So that means A, then I get a B. All right, and we can actually do Claney star on Claney star, and that's the same as doing one Claney star. A with a plus in the power, in the exponent, means A and then A star. So it means there's at least one A. That's what A plus means. Plus is in the power. It is not on the line. If it's on the line, it means or. Okay? Okay, if you get something like this, it means that I have AB star. By the way, I'm seeing that there's an error in your packet on page 1 at the very bottom. There's rule number 4, and it actually is supposed to have a plus in between the A and the B and has a star like that. And so it's actually trying to tell you this rule. So if I get AB star, that means that if I get any letters at all, it has to be a pair, an A followed by a B. I might not get any, but if I do, it's going to be like AB or ABAB or ABABABABAB. I can't get any single characters. Okay, so this is always in pairs. All right, let's do this. A plus B star, BB. Let's see if we can make a finite state machine for this. So I'll do one example, and then I'm going to have you guys do an example. So we always have a start state, and by the way, you can show the start state as an arrow coming from nowhere going into the start state. All right, we have to get an A to begin with. You don't have to give your states labels. You can give them numbers. It's totally fine. Okay, and then I might get an A or a B. Probably doesn't change very much, right? So let's do this. Put A comma B there, and a star always has to have some kind of loop, whether it's a loop that goes to another state or not, has to have a loop. And then I have to get a B, and I have to get another B, and this is an accepting state. Is this a deterministic or a non-deterministic state machine? This is non-deterministic because there's a B going out from 1 to 1, and there's a B going from 1 to 2. Yes? Can anyone answer the question why 3 is an accepting state in this finite state machine? Yes? Right. If I'm in state 2 and I get an A, I'm going to go back to start because I don't have a string that's in the right format. So anything that is in the right format will be able to follow this path. So it'll end in BB and it'll start with A. So every string that actually can get to 3 is in the format that I want. I am not going to spend time. There are ways to actually turn non-deterministic finite state machines into deterministic finite state machines, but we're not going to spend time on that because we don't have a lot of time. So you can look that up if you're interested. There's plenty of pages on the internet about that. Did you have a question? Yes?
How does the machine know when it receives a B whether to stay in state 1 or go to state 2?
The question is, how does the machine know when it receives a B whether to stay in state 1 or go to state 2? It does not. That's why it's called non-deterministic. Yes? That is one possibility. So we can actually make this deterministic by getting rid of this, right? And send it over to 2 if it gets a B. And if it gets an A, send it back to 1 because it didn't get 2 B's in a row. So sometimes turning a non-deterministic machine into a deterministic one is very simple. But I'm not going to count off if you make me a non-deterministic machine for a regular expression that I give you. So you just have to make a finite state machine. I don't care if it's deterministic or not. Okay, so let's do a couple that have ORs in them. For example, so by the way, if you see this, there's this little kind of splat symbol in your handout, at least on this computer. It looks like a times, but not the same as the star in the power. That means OR in your handout. So in the finite state machine packet, that's an OR everywhere you see it. I'm sorry, the character's not coming out very well. But maybe try the PDF. This is the Word doc version, so it's probably using a different character set. Okay, so if I do B star or C, that's a regular expression, and I should be able to write a finite state machine for it. So let's do that, and then I'll give you guys one to do. So we have our start, and then we can either get some B's or we can get a C. So we don't want to make the starting state an accepting state and then go somewhere with it. So let's just make B star. So this right here is a B star machine, right? Does everybody see that this is a finite state machine that takes the language B star? Okay, good. Let's make a separate one that takes the language C. Okay, now, when I put two machines together, you can combine states if they make sense. The trouble with this is that the start state here, I can't just combine the start states because this one's an accepting state, but that one's not. Right? So what I might want to do is have a start state. And definitely if I get a C, go to my got a C state. And what else can I do to put the B star on there? I can make a state for B star, right? Okay, so that makes sense for getting some B's. How do I get to that state? With a B? That'd be good. Now there's one string that this machine doesn't take, that it needs to take. The empty string. So, the empty string can go to the B state. Again, this is slightly non-deterministic because if the empty string, the empty string means anytime I'm in the start state, I can just jump to the B state. And it means you can't take a C, but that's why it's slightly non-deterministic. But this is not too bad. But we didn't want to make the start state and the accepting state, although actually we probably could have, and it would be the same thing. Okay, so you can combine two machines just by hooking them up with a transition. So actually you can just make an empty state transition in between them also. An empty string state transition. So you could just put these together. So in fact, I actually also could just do that. Yeah, it will. So it will take some extra stuff. So you start with that, but then you have to fix it with accepting stuff. So you can connect to with a plus, but then you have to fix accepting states. All right, let's have you guys do one. Okay, so I'd like you to make a finite state machine for this regular expression. Here's my solution with the state transition table. So I've numbered the states because writing them all in the transition table is too long. So I number them 0, 1, 2, 3, 4. And a dash means you don't go anywhere. That means if we had the bad and wrong state, we would go to that. If we got those other characters. So if I get an A, I go to state 2. That's the starting state. So my language was here. Okay, so if I got an A, I got an A state. And then if I got another A, I went to, hey, I've got some odd A's. So if I get anything else, it better be another A. And then I'm going to go back to the got an A state because now I'm allowed to get a B after that and be done. Or from that state, I could have gotten a BB pair. And the reason why they go back to the same state is because here I can either go to AA or BB, and I can alternate them as many times. It might be 0 times. So when I have a star, I usually come back to the state that got me to where the star starts. And then I usually, the things that come after the star come after that state. So the star leads out to some stuff, and the stuff has to come back, and then you can go to the things that come after the Claney star. All right, that's it for today. Question? Yes.